All right, let's get started today. So in this video, we're going to discuss a very, very powerful technique, not just in electricity and magnetism, but in physics generally speaking, and that is Gauss's law. So to get into this, first thing I want to do is discuss a particular thing called flux. Flux is basically figuring out how much of some entity passes through a particular part of a surface. So for instance, let's say you have some kind of a patch. Maybe this is water, maybe this is a window, whatever this is. So you have some square patch. I have it kind of horizontal, let's say. And we want to know, let's say it's raining, and this patch is your part of your swimming pool, and you want to know how much of the rain water is going into the swimming pool. Well, that can be thought of as calculating the flux of the rain through this patch. Maybe this is the top surface of the water. And so how would we do it? Well, generally, if we're going to do this mathematically, what you need to find is, if this is your area, this is kind of the opening, the hole, the particular patch that you're thinking about, then you want to know how much of some entity, let's say the rainwater, goes into that particular region, that surface area, that area. Well, you want to know, this entity, let's say the rainwater, it could be going straight down perpendicular to the surface, which would be excellent. Maybe you have the water flowing straight downwards vertically. And so all you would have to do is count up how many raindrops are hitting this piece of surface. Not too bad. You would just add up, sum up, all of the raindrops that go through this particular area. Well, how much is that? Well, it's the number of raindrops total, because remember, you may have rain over here, and over here, and over here. You're going to add up all the raindrops, but only the amount of the rain that's going through this particular area. Okay? So the flux, and the symbol for flux, I'll write it like this, is going to be kind of like a sum. You're going to be adding up a bunch of terms, and what you're adding up is how much of this stuff is going through that particular region. You don't want any of the other stuff. So all of these other raindrops that are coming over here, they don't count. Okay? But you also have other problems. For instance, maybe you have the rain coming in at angles. Maybe it's windy. And so the rain isn't just coming straight down, but you may have a raindrop that started here, but it just happens to hit your region by the time it gets there. So we also have to worry about what happens if this particular element, this thing, is not coming in perfectly normal, perfectly perpendicular to the surface we're talking about. The way we do this is first something interesting mathematically, and that is to say, look, we have this region that we're discussing. Obviously, the bigger the region, the more rain is going to go through it, and the smaller the region, the less rain is going to go through it. That makes perfect sense. So obviously, the flux should depend on how big of a region we have, and so it should depend on the area that we have available. What's catching the rain? The bigger the region, the more rain we're going to catch. Also, if all the rain is coming nice and perpendicular to this region, then we're going to get a lot more. But if the rain is coming in at an angle, then a lot of the rain is going to miss just because it's not coming straight down, it's coming at an angle. So it should also depend on the angle. Okay, that makes logical sense. Now, how can we find that amount of rain which is coming in nice and perpendicular? Right? So, for instance, if you remember in normal classical mechanics, we have the floor, we have a box, and we want to calculate the work done by a force in pushing the box. Right? So maybe you have a force F, and the box is going to travel horizontally to the right, and maybe this box travels a distance of X meters. We want to calculate the work. Well, we know work is the amount of the force, which is in the same direction as the motion of the object, times how far the object moves. Okay? Formally, mathematically, what we do in those cases where maybe the force is at an angle, so maybe the force is like this at some angle theta, well, what we do is we say, in order to figure out only the amount of force which is going into creating work for us, we only want the force in the correct direction. Mathematically, there's an operation that allows it to do it, and that's called the dot product. So we say the dot product of the force vector times the distance vector traveled by the object is going to give us how much of the force is in the direction of motion times how far the object went in that direction. So this dot product is a very powerful tool of mathematics to kind of take the total entity which is occurring and only pick the part of that entity you care about, which is the part of the entity in this particular direction. Well, we want to do the same kind of a thing with this problem, with our flux. We say, look, some of this rain is coming in at an angle, maybe all the rain's coming in at an angle, but we only want to know how much of the rain, the component of the rain, which is coming in nice and perpendicular. Or instead of rain, maybe you think of wind, a continuous flow, or water, a continuous flow of water. We want to know how much is going through this area. That means we want to know how much of this water, or wind, or air, or whatever, is coming perpendicular, the component which is perpendicular to the surface. So the way we're going to do it is we're going to define something, and that is the area of a surface as a vector quantity. Okay. So if we have, let's say, a little box like this, maybe there's a path or something, but there's a box, and there's maybe this is some length x, and this is some length y. The area as a vector is going to be, of course, x times y, but because we want to make this a vector, so this is magnitude, what we want is some directionality associated with the area. And we have options. What should the area's direction be? It's kind of a weird question to ask. How can an area have direction? Well, it's because we're defining it the way we want to define it because it's useful. So what we're going to do is we're going to define the area as a vector to have a direction which is perpendicular or normal to the surface itself. And so if this is the little window, the area is pointing out or in, depending on which direction you want to make the positive direction. And so that's how we'll call this, let's say, the n hat direction, where n means normal. So the area vector is going to be the area with some directionality associated with it, and we're going to define that direction of an area to always be perpendicular to the surface, okay, normal to the surface. Once we have created area as a vector, now what we can do is say, okay, let's say we have some field. Remember what a field is? And let's say it's a vector field. That means everywhere in space you have these arrows, these vectors that tell you the magnitude of the field and which direction that field is pointing at that particular location. So we have all these vectors out in space, and then we're going to take, so maybe it looks something like this, all these vectors pointing like this. And then we're going to say, okay, in this part of the space, how many of these arrows are pointing through that window, through that space there? So the way we get it is we say, okay, we have our vector field. Let's call that vector field E. Okay. And we want to know how much of this vector field E points straight through this window. So we're going to do the dot product with our little area vector. Okay, so if this window has an area, let's say the area is pointing away, pointing that way, and we want to know, okay, well, how many of these arrows are in the same direction, because that's the arrows that are going through the hole, through the surface. How many are in the same direction? Well, just like over here with work, if you want to know how much force goes into work, it's how much of the force is in the same direction. We do the dot product. Same thing here. You have this vector field out in space. You're going to take a little area of space, and you're going to say how much of these vectors points through this space in the direction, perpendicular to the surface. Well, we just take the dot product of the little area element of space with the vector field we're talking about. Okay? And that's what flux is going to be. More formally, flux of some field E, let's say. It doesn't have to be E. I'm just pulling a number or a letter, and we'll see why I'm pulling E, but it could be any vector field. The flux is defined as the integral, because we're going to add up a whole bunch of things, of the vector field we're talking about, dotted with the little area element we're discussing here. So if we have a full, huge, maybe a big old surface like this, and we want to know, okay, well, how many of these arrows are going through this surface? Well, what you're going to do is you're going to break this big surface up into little grid patterns, little squares. And on each little square, you're going to calculate the area of the square. That's my little dA. And we're going to do a dot product of that with the amount of the vector field which is going through that little bitty square. And we're going to do that for each one of these squares and add up all of those together to get the total flux through the whole sheet. That's what this is telling you. You take little bitty squares, each one has little bitty areas, and we create a vector out of those areas so they have directions. And then you say, on each one of these little squares, how much E is pointing straight through the square. That's the dot product. And then we're going to add up each one of those squares together to get the total effect. And that thing is what we call the flux. How much of this E field it goes through this A element, or the A surface itself. Okay, once we understand what flux is, now let's look at this. If you remember, we said, okay, here's a coordinate system, and let's say we have a charge, Q, right there. And maybe I want to know, what is the electric field right here? Okay, so find E, the electric field, at this location, and I'll call that location some r distance away. Okay. Well, how do we do it? Well, if you remember, electric field is 1 over 4 pi epsilon naught. Q, the little charge that's creating the electric field, over r squared, where r is the distance from the charge creating the electric field to where it is we're measuring the electric field. Okay, that's the electric field. I won't put the little arrow on it because I don't have the unit vector, but Of course, we could create a vector out of it by doing that. That's no big deal. So we remember that's the electric field, right? Okay, now let's look at this. Let's do something slightly different. Now what we're going to do is we're going to, if I want to know the electric field at this location I marked on the coordinate system, watch what happens if I say, okay, let me make a little circle that goes through the point I'm interested in. So this circle, or let's make it a sphere. I'm going to pretend we're in 3 dimensions, right? So we have X, Y, and Z directions. So we have this sphere that I drew around my charge Q. Q is at the center of the sphere. And the size of the sphere, the radius of the sphere, is such that the outer layer, the surface of the sphere, goes through the point I'm interested in. All right. Now what I want to do is I want to say, okay, what would this be equal to? Now, I'm going to give the answer instead of going through the full derivation. We're going to look at how this is derived later on. But for now, we just want to use this as a way to calculate for now, just to make problems a little bit easier. What should this be equal to? It turns out that what this is equal to is the total charge enclosed by the sphere divided by epsilon naught. Okay? That's my claim. And let's see if this happens to work. All right, so how do we solve this equation? What I want to do is maintain, or see, is it true that the electric field is indeed this? Or I should say, we know that it is that. The question is, will this reproduce that equation? And if it does, then we'll see why we want to do this. We'll see why this is powerful. So let's determine it. I want to find E and make sure it's equal to that stuff. So let me go over here, and I'm going to say, okay, integral E dot dA is equal to the total charge enclosed over epsilon naught. Now let's look at this integral. E is of course a vector field. A, that's our area. And what do we mean by that? Well, we mean take a little area element of this sphere and find out how much of the electric field is going through that amount of area. That is the dot product of the electric field dotted with the area element at that location, and then I'm going to add all of these things up all over the sphere to get the total. Well, okay, what do we know about the electric field of a point source? Well, I know the electric field of a source of a charge, a single charge, is radial. All the electric field lines are coming out straight from it. They don't curve, they don't bend, they just come straight out of the charged particle. So everywhere along the surface of this sphere, whenever one of the electric field lines crosses the boundary, it's always the same amount, because we're calculating the electric field at a constant distance from the charge. If some of the parts of the sphere were closer to the charge and other parts were further away, then of course that's not true. But because the electric field is equal in all the directions for a point source, then everywhere on the boundary of the sphere, you have the same amount of electric field trying to come out. So the electric field in this case, at this location, is constant in terms of its number. So I could pull it out of the integral. And I say, okay, well, it's just E times the integral of dA is equal to Q enclosed over epsilon naught. Well, what's the integral of dA? Well, it's find the little bit of area, this little bitty window here, and then add all of those windows up to get the total. That's what this integral is telling you. Well, if you add up all the little pieces of the sphere, you get the full sphere. So this integral of dA is just the surface area of the sphere itself. And it turns out the surface area of the sphere is just 4 pi r squared, where r is this distance, the radius of the sphere we're talking about. All right, what's on the other side? It's our Q enclosed. Well, look at our sphere. How much charge is inside of the sphere? There's only one charge sitting there. It's just little q. So Q enclosed is just a little q, and we divide by this number epsilon naught. Okay, we're almost there. All I need to do is solve this equation for E, and what do I find? E is equal to Q over 4 pi r squared epsilon naught. And now look, these two things are identical. 1 over 4 pi epsilon naught, there it is, 4 pi epsilon naught in the denominator. Q on top, r squared on the bottom. And so yes, this does work. It turns out that we get back the exact same equation for the electric field of a point source using this new technique. Somehow, this is telling us that the amount of electric field you find escaping out of this boundary, we put a little boundary like a little shield or something, covering up the charge, so we can't see what's inside of it. If all I do is detect how much stuff is coming out of this sphere, that should tell me about what's inside the sphere. Obviously. If you have a heck of a lot of electric field lines coming out, that means you have a heck of a lot of charge inside. But if you only have a little bit of electric field coming out of the sphere, then it means you only have a little bit of charge inside. So this makes intuitive sense. The more charge you have inside of this region, the more electric field flux you're going to have. And what's really nice is that, yes, I chose a sphere. I wrapped a sphere around this charge, but it doesn't have to be a sphere. It could be any shape I want. The reason I chose a sphere is because the area of a sphere is very easy to do. If I did some weird shape, I'd still get the right answer. The problem is calculating the area of this weird shape, I don't know how to do. So you should always, given a problem that uses Gauss's law, choose that shape which is easiest for you to calculate what you need. Sometimes it's a sphere, sometimes it's a rectangle or a box. It just depends on the particular situation. Now, before we continue, we have to make sure there's nothing wrong here. For instance, think about this. Let's say I have my sphere. Here he is. And I've got no charge inside, but I've got a charge over here somewhere. And I'm trying to figure out what's the electric field there. Or, yeah, we'll do this. You say, oh, wait. This charge is this charge, Q, is creating an electric field in all directions, right? So, if I'm looking over here, notice I can have a field line that comes into the sphere here, goes through the sphere, and then comes out of the sphere over here. So you say, wait, but there's no charge enclosed here. So if there's no charge enclosed, remember the flux is giving us, which is integral E dot dA, is telling us the amount of charge inside of this surface. There's no charge in there. Maybe this is our coordinate system there. But I'm getting this electric field line coming out. Doesn't that violate the properties or what it is we're trying to do? And the answer is no, because notice, for every field line that comes out of this side, that same field line had to come in from this side. So you get some positive flux, some amount of electric field coming out, but you also had a negative flux, an amount of field coming in. And the amount that came in is the same as the amount that goes out. So you get a total net flux of 0, which means you have a total charge inside of 0. So this works even when you put some shape, in this case a sphere, not around a charge, but charges are outside the shape. The question is, well, what how much charge is inside, you don't have to worry about it because everything works out. If the charge is not inside, the net flux is zero. You have stuff coming in and stuff coming out, and they balance. But for this problem, where the charge was inside, notice every one of these arrows is coming out of the sphere, and there are no arrows coming in. So this works. It works perfectly fine. Now, what about, why would we want to do this? Why don't we just use the normal equation, this one right here? We got the equation. Why do this other method that has an integral in it when we just write that down? Well, notice, what if we have something like this? You've got these three charges, Q1, Q2, and Q3. And we want to know what's the electric field right there. Okay, maybe we have a coordinate system like this. Well, this is not so easy. Notice we have three charges. Each one of these charges will contribute some amount of electric field. We have to add all of these electric fields together to get the total electric field, but each one of these is a vector. So I have to add three different vectors together. Each one of these vectors is probably in some weird direction. So that's a lot of calculations I have to do, a lot of x and y components and all of that. However, we could cheat the system and say, look, let me just wrap a sphere that goes through the point I'm trying to calculate and encompasses all of those charges that I care about. Okay, so there's my sphere there. Now all I have to do is, just like I did before, the flux of the electric field should be the net charge enclosed over epsilon naught. So, okay. Well, again, for each one of these things, every point along this sphere, the total electric field is the same. So we have E times the sphere, 4 pi r squared, is equal to the total charge enclosed, that's Q1 plus Q2 plus Q3 over epsilon naught. And again, we get the same kind of an answer. This, unfortunately, though, is not going to be a vector quantity. This is going to give us the magnitude of the electric field, but it will not give us the direction. But that's okay. If we need the direction and everything, there's things we can do. Or you can just do it the old way with vectors. But here's a more interesting problem. Let's say we have this example. Very difficult problem, generally speaking. You have a solid conductor whose total charge is Q, capital Q. Okay? We're going to say this conductor has a constant charge density. What does this mean? This means at every point I go to calculate the amount of charge on a little piece of this sphere, this conductor. Here it is right here. I'll draw it. Here's my little sphere. When I go take a sample of the sphere, I take a little piece of it off, and I go measure how much charge is there, I get a certain amount. Then I go take a different piece, same amount of piece, the same size of a piece, but somewhere else, and I calculate the charge of that piece, it's the exact same. So you have the total charge is distributed evenly all throughout this spherical conductor. Okay? And we're going to say that charge density, we're going to give it a name. Let's give it the name rho. Okay? That's the volume charge density. How much charge is spread out, or the density of the charge spread out throughout this conductor. All right. And let's let the conductor has constant charge density rho and radius. Let's say it's radius R. that'll be fine. All right, the question is, number 1, or part A, calculate E at point B, or point A, I'm sorry. And then for B, we'll calculate the electric field at point B. And when I say that, here's the picture. Here's our conductor, here's our sphere of charge. And I'm going to say point A is over here, and point B, so here's our coordinate system, point B is in here. So it's in the center, not in the very center, but somewhere inside of this solid sphere of charge. And I want to know what's the electric field at these 2 locations. Okay? So let's do part A first. Okay, so let me redraw it. Part A. Here's our spherical conductor. Here's point A I care about. There's the conductor. And so let's let the distance from the center to point A be A, of course. So A meters away. And we know this sphere has radius r and constant charge density rho. And I want to know how much electric field is going through this point A. How do we do it? We use Gauss's law. We draw a surface around our interesting object that goes through the point I'm trying to observe. So A I'm trying to observe, so I'm going to draw my little sphere all around this particular thing. Okay. And now I say, Gauss's law says the integral of E dot dA is equal to the total charge enclosed over epsilon naught. All right, well, how do we do this? We say the electric field, again, is going to be constant. We could pull this out of the integral. So we'll have E times the integral of dA, which is 4 pi r squared, is equal to, or sorry, not 4 pi r squared, 4 pi a squared. Remember, this is the radius. The dA is the surface area of the fake sphere I drew around the real charge. So the real charge has radius r. I drew this imaginary, what's called a Gaussian surface, this imaginary surface, so that it goes through point A. It's encompassing the whole thing. So the area of my imaginary Gaussian surface is 4 pi times a squared, because a is the radius of that sphere. What's that equal to? That's equal to the total charge enclosed by my sphere. Well, I'm told by the problem the total charge of this conductor is Q. So Q over epsilon naught. I solve for E, and what do I get? E is equal to 1 over 4 pi epsilon naught Q over a squared, which is exactly what we would expect. I'm looking at distance A away. I want to know what's the electric field. And notice it's very nice. We get exactly the same answer as if what we were working with was a single charge. But instead of it being a single charge, it's some big bulky thing. But when you're far away from that big bulky thing, it seems to act as if it's just a single point charge whose total charge is Q. Very, very nice. And that makes sense, right? If you have a tennis ball in your hand and you look at it, it looks like a tennis ball. It looks round and it's got its own volume. But then someone stands 500 feet away holding the tennis ball. Well, now it just looks like a little point. You can't really see it too well because it's too far away. So to your eyes, you don't see it as a whole sphere, you just see it as a point. And that's what's happening here. We have a nice spherical charge distribution, but because we're looking some distance away from it, to us, that sphere just looks like a little point. And of course, the farther out you go, the more this is true. If you get a little too close, then the numbers don't work perfectly well, and you have to have some modifications. But for distances big enough compared to the conducting size, this works perfectly fine. Now the more interesting one, part B. Part B, remember, we have our spherical conductor. Here it is. Here's the center of the sphere. And maybe I want to know here at distance B, what's the electric field there? Okay, now this isn't quite as easy, but we're going to go through the same technique. Gauss's law says the integral of E dot dA is equal to the total charge enclosed over epsilon naught. Okay. So what do we want? Well, let's do another Gaussian surface just like before. Again, for this particular problem, the surface I'm going to draw is a sphere. But now the sphere again has to go through the point that's interesting, which is this B. So the sphere looks like this. So there's the sphere. The radius of this sphere is B. And so I want to know, okay, what's the electric field there? Well, it's E times the integral dA is equal to the charge enclosed by this. Now this is, well, let me leave it like this for now, over epsilon naught. So what is the area of my little Gaussian surface? Well, it's just like we did before, E times 4 pi b squared, right? And now this part over here, I'll put 1 over epsilon naught in front. Now I need this Q enclosed. Notice now there's a lot of this conductor that is outside of our sphere. And all of that amount of charge being outside, not enclosed, does not give us any electric field. Or no net electric field, I should say. It cancels itself out with other regions. So I only want to know how much is inside of this sphere. How in the world do I figure that out? All I know is that the total charge, if I add all the charge up, I get Q, and I know that it's got some constant charge density. So the way we're going to do it is this. Because we know the charge density is rho, then what we could do is we could say, if we have a sphere, we take a little piece of this sphere, a little box, and we say, okay, well, how much charge is in this box? Well, it's the density of the charge, or rho, times how much of that rho do we have inside of this box. So it's rho times the volume of this little box, because remember, rho is Q over volume. So the little bit of Q that's in this little bitty box is going to be the total rho times the volume of the little bitty box we're talking about. And we're going to add all these things together to get the total charge. But we don't want the total charge. We only want how much is inside of our little red region here, our Gaussian surface. So we're going to say it's the integral, the adding up all the pieces, integral of our rho times our dV, right? We're going to take our sphere of charge and we're going to break it up into a bunch of little bitty boxes. Each box has a little volume dV, and we say how much charge is in that little box? Well, it's the charge density rho times the volume of that box is the charge in that box. And then we add all those little boxes together to give us how much is in this region. So we're told rho is constant, so we could take it out the integral. And so we'll have integral of dV, which is just the volume that we're talking about. The volume we're talking about, here's our 1 over epsilon naught, here's our rho. The volume of our region that we're interested in is 4/3 pi times b cubed. Right? That's the volume of our Gaussian surface we created in here that goes through the point B. So it's got radius B, and it's a sphere. So the volume of that sphere is 4/3 pi b cubed. And now we have this is equal to this. Let's solve for E. We get E is equal to, well, the 4's cancel, the pi cancels. B squared cancels with B cubed to get just B. And we have E is equal to rho times B over 3 epsilon naught. And there we go. I now know the electric field that's within this spherical charged conductor at the point B, inside at radius B. And of course, if we were to extend B all the way out to R, then we would get the total charge and we'd get our normal electric field thing. Now, if you look online or you see other professors do this, sometimes what they'll do is they'll stick in the fact that rho is Q over V. So this rho right here, they won't leave it as rho, but they'll put Q, the total Q, over the total volume there, and have it in terms of little r and b and things like that. If you want to do it that way, that's fine too, but you could just leave it as rho because you're told in the problem the charge density is rho. So just use rho. There it is. So this is a very powerful technique because think about how difficult of a problem this is. You have a solid sphere of charge. That means you have trillions and trillions of charged particles in there. Lots of them. Each one is at a slightly different angle and a slightly different distance from the interesting points I'm talking about. And they're all going to be vectors. Electric fields are vectors. I'm going to have to add all these vectors together, x and y components, magnitude and direction. That's a very complicated, time-consuming problem. However, through the use of this Gauss's law, notice how quick it is. Look how easily I was able to solve this problem. 3 lines, and that's only because I didn't want to skip too many steps. And even this one, that's even more complicated, because some of the charges are outside, some of them are inside, some will cancel with each other. All of that is taken care of just by using Gauss's law. Now, you're going to find other versions of Gauss's law too. For instance, you can have a charged sheet instead of a sphere. So this sheet has a bunch of charge all over it. And maybe you want to know what's the electric field over here. Well, there's a Gauss's law for this too. It's the same Gauss's law. It's still integral E dot dA is equal to Q over epsilon naught. But now, instead of using a sphere to go around everything, now we're going to use what's called a pillbox. So it's like a little rectangular box that goes through. And you're going to do the same thing, only now the area will be the area of the box instead of the area of a sphere and things like this. But that's just because the geometry of this problem is different than the other. The other problem had spherical symmetry. This problem does not have spherical symmetry. So instead of using spheres, we use the Cartesian coordinates, and so we use boxes. But the thing is the same. We want to know what's the electric field at this point. How do we do it? Well, we wrap a Gaussian surface that goes through the point we're calculating for. It's going to enclose some amount of charge, maybe all the charge, maybe not. And so you say, okay, the amount of electric field that goes through my fake Gaussian surface is going to tell me how much charge is inside of that Gaussian surface. And we use that to get our E. So very, very nice, powerful technique. Matches what we did before, only now we could use this for the more and more complicated problems. So practice this for sure. You can have spherical shell. So we did a solid sphere, but we could also have a sphere that's like a basketball. So there's only a surface, but the inside is hollow. So all the charge is just on the surface. We could have that. And so if we were to try to find at point B, like we did before here, and we did our Gaussian surface, well, if this is a hollow sphere, there's no charge inside. So you should try this problem. Try calculating, uses Gauss's law. Call this point B. This is the radius of our actual sphere. Let all the charge be on the surface, a total charge of Q. And you say, okay, at this point inside this hollow sphere, what's the electric field? You should get the electric field is 0. Why? Because there's no charge inside here. All the charge is outside on the shell, on the surface. Okay? So try it out, make sure you get it. If you don't, then definitely let me know, ask me, show me what you did, and we'll see where you're going wrong. But other than that, that's all I wanted to go through for Gauss's law. I will see you next time.